before starting, any questions if you have? No? Guys, remember one thing, during the explanation, you can raise your hand, or if I happen to not see your hand, you can just, unmute your mic and you can excuse and ask the question anytime during the explanation, okay? Don't wait till the end of the explanation to ask questions. So let's start our class. So, okay. So if you remember, in the last class, so in the last class, we looked at the different materials, conductors and insulators, and we looked at the properties of the conductors and the insulators both. Then we looked at the definition of the relative permittivity, dielectric constant, dielectric strength, and then we looked at the current and the current density, the two types of currents, the two type of current density, conduction current density and convection current density. And then we took the Ohm's law, and then we looked at the current continuity equation, which basically states that any current density which is leaving out a closed surface must be equal to the depletion of the charges with respect to time inside the closed surface. So, or in other words, in differential form, it is del dot J bar is minus dou rho V over dou T. And it is again saying that there is no accumulation of charges, because inside, if you don't have any charges, then whatever is entering this closed surface must leave. So that is the current continuity equation. And then this last part tells us that, if you place a charge on a conductor, then the charge will rearrange in such a way that it will only appear at the surface in the form of a surface charge. And now remember one thing, the conductors, please do not confuse for the isolated conductor and for the conductor which is connected in a circuit. So these properties, what we talked about is for the isolated conductor, and once it is connected in the circuit, the properties will change. For example, if your conductor is isolated, then you cannot have an electric field inside the conductor, because the conductor is in static equilibrium or electrostatic equilibrium. That is, the positive and the negative charges inside, they rearrange in such a way that they induce the electric field which cancels out the external electric field, and it will be zero. This is for the isolated conductor. But when the conductor is not isolated, for example here, when the conductor is connected to a voltage source, then we don't have these equilibrium. So therefore, in this case, you will have the electric field inside the conductor because of extra charges which are coming here and going from here because of this voltage source or electromotive force. And because of this change in the charges at the two ends, you will have field. You will have the electric field inside the conductor also. Again, the equilibrium is lost. That's why. So you have the electric field, and because of this electric field, you will have movement of charges, and that is your conduction current. So J is equal to sigma E. This expression is essentially coming from the movement of charges inside the conductor, and this movement of charges is because of the force that the charges are seeing because of this electric field. And the force you can from the force, you can get the drift velocity inside the conductor. And then eventually you will see that the drift velocity will also be a function of electric field. And hence the current density J is equal to sigma E. So you can go through these, this definition and this derivation here, see, and remember, this is how the current density. So the current density general expression is nothing but it is the charge density multiplied by the velocity. So here the velocity will be the drift velocity because we are inside the conductor. So the electrons will move from it will have a lot of collisions as it moves because of the atoms present in the conductor. So this is the conduction current density. In convection current density, it is simply rho v times u. So this is what we have seen in our previous classes. I'm just, slowly reviewing everything. And now we went to the boundary conditions. And in the boundary conditions, we looked at the first boundary condition where we tried to figure out how the electric field components will experience when an electric field moves from one medium to another medium. And what we saw is, if you remember, we kept our boundary along the x-axis. That means my xz is the boundary. So this is my z. So in a way, xz is the boundary. So if you see here, if you look into the 3D, so this is my x direction. This is my y direction, and this is my z direction. So this is my boundary. And then what I did, that the region above has epsilon 1 as the medium, region 2, which is below, has epsilon 2, and then we put a hypothetical closed line, and then we try to apply the rule which an electrostatic field must satisfy, which is the closed line integral E bar dot dl is equal to 0. And then the length is delta x, the height is delta y, and this is the direction. And then what we did, once we have this 4 lines, we said that we want to look at the boundary, right? That means just above and just below. So if this is, y is equal to 0, this is 0 plus, and this is 0 minus. That's why we took delta y and we made delta y going to 0. So that means we are reducing the height. And because of this, 2 integrals vanished, which is integral 2, 4 and integral 2, they both vanished. And then we end up saying that E1x is equal to E2x. That it says that the x component of the electric field E2 will be same as the x component of electric field E1. So what does this mean? This means that the x component, so if your E2, this is the x component of E2. So this is your E2x, AX. This is the x component, right? Sorry, it is already in vector, so I do not require this arrow. So this E2 x, AX, and yes.
This shouldn't be Z, right? It should be Y. The 3D you draw.
Just a second. Which one? This is X, this is Y, and this is Z. This direction is Z.
Z is out of the
Yeah,
sheet.
it is out of the paper. So now I am now tilting it a little bit to the left. So this is X, this is Y, and this is Z.
Okay.
Correct? So now what I'm saying is this E1X is equal to E2X. What does this mean? That means the component of E2 in the X direction, E2X, and the component of E2 after the boundary, which is E1X, AX, they don't see any change. They don't see any change. That means they don't see the change in the medium because their values are the same. That means E1X is equal to E2X. This is the meaning. And now if you go and if you closely look at what is E1X, E1X is nothing but if this is my boundary, then my E1 is sitting in this boundary plane, right? See this blue one? It is sitting in the boundary plane. So it is nothing but it is called as tangential component. Remember the definition of tangential? Tangential and normal is with respect to the plane. And when we say perpendicular is usually with respect to line. So now with respect to plane, tangential are nothing but those components which are residing in the plane. Those components are called tangential, and the component which is perpendicular to the plane is called as nothing but normal to the plane. So if you see here, E1X is sitting in the plane. So E1X will sit in the plane, and yes, and what else will sit in the plane? Which component will sit in the plane? Can anybody tell?
Z.
Z, yes. So if I want to see it in the boundary, this sorry, let me not write E, let me just write X. So X direction is sitting in the boundary on the boundary plane, and Z direction is sitting in the boundary plane. So that's why this X component and Z component are called as tangential component, whereas Y component is 90 degrees to the plane, and therefore Y component is called as the normal component. Okay, so therefore we with this boundary condition we found that E1X is equal to E2X. That means now I'm generalizing and I'm saying that E1 tangential is equal to E2 tangential, because you can do the same thing while considering this side and you will get the same answer. So that's why I'm generalizing it as E1 tangential is equal to E2 tangential. That is, the tangential components of my electric field will not experience any boundary. So whatever value they have in this region, they will have the same value in this region. So this is the first boundary condition. That is, the tangential components of the electric field is continuous across the boundary. When we say continuous, we are trying to refer saying that they will not change any value. This is the first boundary condition. Now, second boundary condition, what we are doing for the second boundary condition, now we are trying to apply again, say, Gauss's law. See here, this is my boundary. So this is my boundary. Now, what I am doing is this is my X, this is my Y, this is my Z. And now my boundary is this plane, which is my XY plane. See, this is my boundary, the XY plane, this one. Now I have an electric field in this region. This is my region epsilon2, which is Y less than 0. Z less than 0, Z less than 0. and Z greater than 0 is my region 1, epsilon 1. And here I have an electric field. Instead of field, I am using electric flux density, T2. Here I am using electric flux density, D1. Okay. So now what I am doing, I'm applying the second, important law that your electrostatic field must satisfy, which is your Gauss's law. So when we apply Gauss's law, what we are doing is we are now, to apply Gauss's law, we have to enclose it in a closed surface, right? So here my closed surface is this cuboid. And I have placed the cuboid in such a way that half of the cuboid is in region 1 and half of the cuboid is in region 2. So half of the cuboid is above z is equal to 0 and half of the cuboid is below z is equal to 0. And its length, width, and height are, see, delta y, delta x, and delta z. Okay. So now again here, what we want to look at the electric field at the boundary. That means that is at z is equal to 0 plus, just above at this point, and just below 0 minus. So to get this, if you want to find the closed surface integral of d bar dot ds is equal to 0, how many surfaces we have? We have 6 surfaces, right? So we have the top, 1, bottom, 2, 4 sides, 4. 4 plus 2, 6. So total 6. So we should get 6 integrations. See here, from 1 to 6. But now since we want to only, look at here, so what I am going to do in order to, say, bring our cuboid to a volume in such a way that we are near the boundary. So in this case, I have to allow delta z to go to 0, right? I have to allow delta z to go to 0. Then only I will be near this boundary. So when I allow delta z to go to 0, then the contributions from the sides are all gone, because the side surfaces will almost be equal to 0. And therefore, the only 2 surfaces left is my top and my bottom surface. So that's why when I make the delta z tend to 0, I'm ending up with only this 2 integration, which is the top surface and the bottom surface. And let's do it. So this is my top surface. This is my bottom surface. This is d bar ds. D bar dot ds must be equal to the charge enclosed, right? Now, for the top, what is my flux density is d1. So it is d1 over this surface. So what is the elemental surface for this one? The elemental surface for this one is dx dy times az plus d bar. Now what will be the elemental surface for this bottom one? For the bottom surface, it is again dx dy times minus az. Can anybody tell me why it is minus az?
Because if we're talking about the elemental surface, so the plane that we're talking about, its orthogonal unit vector is in the negative z axis.
Is it its orthogonal unit vector? Is it in negative z axis? Yes, but what I'm trying to say is why we are saying the unit vector is in negative z direction. Why don't we take the unit vector in the positive z direction?
Because it should be out of the surface.
Exactly, because it is out of the surface. Why? Because this surface is a, yes,
Plane.
This surface is a
Closed.
closed surface. Yes, guys, please. I have emphasized about this a lot in the initial classes. Yes, I'm making delta z is equal to 0. I'm making it close to 0. So now it is almost like sheets, but still it is a part of a closed surface, right? And we know in a closed surface, the unit normal always has to be taken going outwards. So therefore, for this top one, the outwards will be AZ, and for the bottom one, the outwards will be minus AZ. Did you get my point? So this will be the outwards AZ, and for this one, the outwards will be this direction, minus AZ. Clear? So therefore, for the closed surface, this must follow. For open surface, there is no such rule. For open surface, the unit normal can be either going up or it can be going down. It can be, both are correct. But for closed, it will always be outwards. So that's why here you have minus AZ is equal to Q. Now you know it very well. So it is dot product with AZ. So therefore, the X and the Y component of my D1, when I dot product with AZ will become 0. So only the Z component will stay. So that's why you will have D1Z multiplied by dx dy, because dnz az dot product with dx dy az dot az will become 1. Whereas d1x ax dot product with dx dy az, ax dot az will become 0. So it vanishes. Similarly, d1y dot ay dot product with this will again vanish. So you will end up with this multiplication. And for d2 also, we end up with this multiplication. And your dx dy lengths, we have already seen dx length is delta x, dy is delta y. So it is going from 0 to delta y and 0 to delta x. Now, if you do this, you will end up with d1z, this will be delta x, delta y, and d2z, delta x, delta y. Now for the right hand side, rather than using charge, I'm using charge density. So therefore, because this must be the charge enclosed inside my hypothetical closed surface. So since my hypothetical closed surface, which is my Gauss surface, is cuboid, so therefore the charge enclosed in this cuboid will be nothing but the charge density rho s dx dy, and within this region, which is from 0 to dy and 0 to 2x. And I'm using this rho s here, guys. I'm not using rho v, because we know that as delta x is tending to 0, these are almost now the surface charges, because the volume is concept is like gone because of delta z becoming 0. So that's why I'm using rho s. And therefore, now if I say equate left hand side and right hand side, I will get this. So d1z delta x delta y minus d2z delta x delta y is almost equal to rho s delta x delta y, or d1z minus d2z is equal to rho s. This is the second boundary condition. d1z minus d2z is equal to rho s. Now what is d1z? If we look carefully, is d1z the normal component or the tangential component to the boundary? Yes, it is z component, right? So this is my boundary. This is my boundary. And z is in this direction. So therefore, it's a normal component. So that's why I'm generalizing here. I'm saying that d1 normal minus d2 normal is equal to rho s. d1 normal minus d2 normal is equal to rho s. So this is the second important boundary condition of electrostatics, which is E1 tangential is equal to E2 tangential, the first boundary condition, or in the form of vector, I can say that E1 tangential vector must be equal to E2 tangential vector. Then D1 normal minus D2 normal is equal to rho s. That is the normal component. So now if you see here, now the normal components are not equal, right? Because we are not getting D1 normal is equal to D2 normal, right? So that's why we can say that the normal component of electric flux density or the normal component of electric field at a boundary are discontinuous. We said discontinuous. And now to write this in vector form, d1 normal minus d2 normal is equal to rho s. We write it in a different form, which is this one. We introduce a unit vector an12 dot product with d2 minus d1 is equal to rho s. Now, why we do this is because of the following. Now, d1 normal minus d2 normal is equal to rho s. I'm getting this because I'm entering the boundary from region 2 and I'm leaving the boundary from region 1, right? I'm entering from region 2 and leaving from region 1. And because of this direction, I'm getting d1n minus d2n is equal to rho s. What about the other way? Suppose if I enter from dn, from the region 1, and I leave in region 2, then in that case, what will happen? This will change. It will become d2n minus d1n is equal to rho s. Okay, because of the unit normals that you take for the closed surface. So that means what is happening? Based on the direction of your electric field or electric flux density entering a boundary, your boundary condition is modifying. Your boundary condition is changing. This becomes a little bit, difficult for us, especially when we want to apply boundary conditions to any problems. We need to make sure that which is entering the boundary, which component, which electric field is entering and which is leaving, and based on that, we have to use the boundary condition, whether it is d1n minus d2n or d2n minus d1n. So that's why what we did is we, we removed this ambiguity by defining a unit vector an12 and dot producting the unit vector with d2 minus d1 is equal to rho s. And what is this unit vector? This unit vector an12 is the unit normal vector. It is to the interface and directing from region 1 to region 2. If you remember this, that's it. So it's a unit vector to the interface and its direction is from region 1 to region 2. So in this case, in this particular case, our boundary is this one, right? So therefore, in our case, what will be an12? an12 is the unit vector to the interface and its direction is from region 1 to region 2. So this is my region 1, this is my region 2. So the unit vector will be this unit vector. So this will be an12 bar. That it's a unit vector to the boundary. Okay, actually, it's a surface. So if I see from here, then it should be this one, an12, pointing from region 1 to region 2. So pointing downwards. Now for our problem statement, this an12 unit vector is nothing but minus AC. It's nothing but it's minus AC because this is AZ. So going downwards is minus AC. So this is how you can easily apply. And you do not need to worry about that. You just need to find what is an12 for your problem. And based on that an12, you apply that vector form of the boundary condition, which is this one. Got it? Now we have some special cases. So what is the special cases? If you see here, your second boundary condition is based on the charge density. So that means if your boundary has some surface charges, then d1n minus d2n will be equal to that surface charge. Suppose your boundary doesn't have a surface charge. For example, if you have a boundary between two dielectrics, then in that special case, that is, it's called as a charge-free boundary. That is, it doesn't have any surface charges. In this case, E1 tangential is equal to E2 tangential and D1 normal is equal to D2 normal. That means now I can say that the normal component of electric flux density is continuous at the charge-free boundary. See, electric flux density, not electric field, electric flux density. Because in electric field, again, the normal component of electric field will still be discontinuous. Why? Because D1n will have epsilon 1 here, D2n will have epsilon 2 here, and epsilon 1 and epsilon 2 will not be equal. So therefore, we will not say that E1 normal is equal to E2 normal. So therefore, our the normal component of electric field we cannot say that if it is a charge-free boundary, then E1 normal is equal to E2 normal. Wrong. D1 normal is equal to D2 normal. Okay. Now, when the medium 2 is conductor, okay. So now, when my medium 2 is a conductor, that means you have, think about it, you have an air and then you have some, say, metallic rod or metallic box like this. So electric field is air to the conductor. Then what will happen? So the electric field have an the permittivity of epsilon. Then what will happen? Tell me. So we know that E1 tangential is equal to E2 tangential, right? So we are applying the same thing. E1 tangential is equal to E2 tangential. E1 tangential is equal to E2 tangential. Now, for conductor, what will be the electric field here? Yes, this is E1. So what will be the electric field of a conductor? Yes, guys?
0.
Remember, this is an isolated conductor. It is just placed on a table. Think that you have a metallic box placed on a table. And then your room has an electric field. So that metallic box is an isolated metallic box. So we have seen the rule, right? That there cannot exist any electric field inside the conductor. Inside the conductor. Remember, it's an isolated conductor. So if E2 is equal to 0, then E2 tangential will also be 0. And therefore, E1 tangential minus E2 tangential is 0. That means if this is 0, then E1 tangential is also 0. So this is the rule. That means at the boundary here, you will not have a tangential component of the electric field. Your electric field tangential component will become 0. This is when we apply the first boundary condition. Now, if we apply the second boundary condition, the second boundary condition is saying, that D1, so what it says, the tangential component of electric field in the dielectric, at the dielectric conductor boundary is 0. So the electric field here in the dielectric region, that is in this region, will be 0. This region here, near to the boundary, will be the tangential component will be 0. Now, what about the normal component? We know D1 normal minus D2 normal is equal to rho s. But since my electric field E2 is 0, so can I say that my D2 is also 0, which is epsilon E2?
Yes.
Yes. So therefore, my D2 normal is also going to 0. That means D1 normal is equal to rho s. Or if I want to find it in electric field, that means E1 normal is equal to rho s over epsilon. D1 normal is epsilon E1 normal, and therefore E1 normal is equal to rho s over epsilon. So this is saying that the electric field, the normal component of electric field can exist in the dielectric medium near the boundary, and it is only the normal component, and it has a fixed value, which is rho s over epsilon. So the conclusion is, in this dielectric conductor boundary, at the boundary in the dielectric region near to the boundary, there cannot be a tangential component and of an electric field. The normal component can exist, but that normal component will have this value. So if this is, suppose, your conductor, and this is air. So in air, you have an electric field like this. But as this electric field approaches the conductor, because of the boundary condition, it becomes perpendicular. Why? Because tangential component cannot exist. Only normal component exists. So therefore, this is the normal component. So this also, as it approaches, it becomes normal. If this is also there, so as it approaches, it becomes normal. And if this is there, then as it approaches, it becomes normal. Okay, so this is your second boundary condition for the dielectric conductor interface. Okay, so this was your dielectric and this was your conductor. Yes, Zuhair.
So, Doctor, these relations of electric field and boundaries, where do we use it the most?
You use this the most, especially when you solve, electromagnetic problems for our practical cases. An example. Till now, we are just using for the static case. But you will see in our eventual, towards the end of the courses that we see that you will see that the electromagnetic waves can propagate, and you do not need to have electromagnetic wave always in free space. You can also have the electromagnetic waves in the bounded medium. Bounded medium means, traveling within a medium, within a bound medium, which is, bounded from all the sides. A very good example is an optical fiber. How can a light can travel inside an optical fiber? Why the light doesn't come out of the optical fiber? The reason is it's the boundary condition, because the optical fiber is made up of, so the inside circle, inside cylinder has a different, say permittivity, and the outside material has a different permittivity, and the permittivity is set in such a way that, your light cannot go out. And this is coming from the boundary conditions. Okay. A very simple example, easily understandable. Okay.
Okay, understood, Doctor.
Okay, so this is what I have shown it to you. Now, so let's take an example now. The example is, we have a charge-free boundary, and now we have an electric field, and we only know the magnitude of that electric field. We don't know the components. Okay, we don't know X, Y, Z component. We just know the magnitude of an electric field E1, this E1, and it is making an angle of alpha at the point in medium 1. So this is my point P, and it is making an angle alpha. Okay. So let me make it a little bit bigger. Yeah. So it is making an angle alpha. So guys, it should be alpha 1, not alpha. So it isn't making an angle alpha. Okay. So this is known to us. E1 is known to us, alpha 1 is known to us. Now we need to find the magnitude E2 and the angle it is making at point P2, at the point P, which is alpha 2, but we need to find it in medium 2. So this is a dielectric medium. So therefore, There is no surface charge density. Surface charge density is 0. And this is E1. Alpha 1 is known to us. Can you find E2 alpha 2? This is what the question says. Now remember how we are measuring alpha 1. See, alpha 1 is always measured. The alpha 1 is measured with respect to the normal at the interface, because this is the interface. So this is the normal, and the angle your electric field is making with respect to that normal is called the angle alpha 1. And this is the typical way of, say measuring the angles at the interfaces. So remember, at the angles at the interfaces are always measured with respect to the normal of the interface. Now we need to find E2 and alpha 2. So how can I find the magnitude of E2 and alpha 2? Let us apply the boundary conditions. What does the boundary condition says? E1 tangential is equal to E2 tangential, right? So therefore, can you find E1 tangential here? You don't know the components, but you know its magnitude and you know this angle alpha 1. So can you find its normal component, its tangential component, which will be this component? This will be the tangential component. And this will be nothing but this component. So
yeah, you use trigonometry here.
Yes, trigonometry. You know this angle alpha 1. So you just need to apply trigonometry. This is E1. The length is known to you, E1. Can you find the length of this one? Yes. It will be E1 sine alpha 1, trigonometry. And what about E2 tangential? The same way. This is alpha 2. And I want this component, which is nothing but this component. It will be E2 sine alpha 2 with the first boundary condition. Second boundary condition, it's a charge-free boundary. So D1 normal is equal to D2 normal. Again, you represent this in instead of E1, you now represent it in D1. E2, you represent it in D2. And you find the normal component. This is the normal component. See this one? This is your normal component. And this is your normal component. So it's a cosine. So D1 cosine alpha 1, D2 cosine alpha 2. And once you know these two, that's it. You just use, your mathematics, and then you do divide both these equations. You will get in tan, and then you can find it. And before doing that, can I just change D1 and D2 in terms of E1? Because D1 is what? Epsilon 1 E1. And what is my epsilon 1? Epsilon 0, epsilon R1. Because epsilon R1 is the relative permittivity, epsilon 0 is the permittivity of the free space. That will give you the epsilon 1 of my region 1. Similarly, this is for region 2. Now, if you divide these two equations, you will get tan alpha 1 over epsilon R1 is equal to tan alpha 2 over epsilon R2. And therefore, you can find tan alpha 2 is epsilon R2 over epsilon R1 alpha. This is known to us. This is known to us. This is known to us. And how can you find the E2 magnitude? Use any expression, this or this. So E2 will be E1 sine alpha 1 over alpha 2. Once you know alpha 2, plug in here, you can find the magnitude. So this is an example where, the components, magnitude and angles were given to you. Yes, Zuhair.
Doctor, this problem, it's very familiar. When we came out with its equation, it's very familiar to Snell's law in optical waves.
Yes, actually, Snell's law is coming from here, because this is the fundamental. The electromagnetics is the fundamental. Snell's law used these fundamental laws and then derived what is called as Snell's law.
Okay, good.
Okay, so now let's take this example. This is a very good and comprehensive example with which you can understand, but I will go a little bit faster because now we have understood everything. So it's an example saying that you have an electric field E1 which is given as 10 AX minus 6 AY plus 12 AZ volts per meter. And this is given to me. So this is my boundary. And the region 1 and region 2 both are dielectric. Region 1 is 3 epsilon 0. Region 2 is 4.5 epsilon 0. So this is your dielectric constants. Epsilon R1, which is 3. Epsilon R2, which is 4.5. Okay. Now we need to find E2. So E1 is given to us. So electric field here is given to us. We need to find the electric field here. And also the angle that the electric field makes with the y-axis. So we need to find two things. So we need to first find E2. So what will be E2? And also, you know, the angle that it makes with y-axis. Y-axis is the normal, right? Is the normal to the boundary. So if this is your E2, this is your E2. Oh, sorry, I will not show it here. It will be difficult for us to find. So what it is saying that if this is my E2, then this is your angle that it makes. And if this is your E1, this is the angle that it makes. Okay, so this is your E2 and this is your E1. I cannot put an arrow here, guys, because we have in 3 dimensions. So I really don't know how the direction of the electric field E1 will be. Okay, so this is what we need to find. And then the energy density in the regions. So what will be the energy density here? And what will be the energy density here? And this is problem 5.35 of your textbook. So how you should go ahead? So first apply the boundary conditions to first find E. Angles, we will find it later. So first find E. So what is E? So first we are finding the tangential and the normal components. Yes, how can you find the tangential components? Now, x-axis is my boundary. That means which plane is my boundary?
The x-axis.
The x-axis. In terms of plane, the xz plane. The xz plane at y is equal to 0 is my boundary. So which are the tangential components to my xz plane? Which are the tangential components to my xz plane?
X and Z.
Yes, x and z. See, if I elaborate this in the 3D, it will be like this. So this will be your x. Sorry. This will be your y. And this will be your z. And this is my boundary. So the tangential components will be the x component and the z components because they are sitting in the plane, tangential component. Normal component will be the y component. So therefore, I am now decomposing my electric field into the tangential and the normal components. So first I found the tangential component. So which is the x component and z component is my tangential component. And my normal component is my y component. So I have decomposed. Now I applied the first boundary condition saying that E2 tangential is equal to E1 tangential. So therefore, I got the E2 tangential. Then second boundary condition, D1 normal is equal to D2 normal. I do not need to apply vectors because it's a charge-free boundary. So I know D1 normal is equal to D2 normal. So therefore, epsilon 2 E2 normal is equal to epsilon 1 E1 normal, or E2 normal is equal to epsilon 1 over epsilon 2 E1 normal. And then therefore you get E2 normal value is equal to minus 4. This is how you get the normal component. Okay. And once you know the normal component, your E2 is nothing but E2 tangential plus E2 normal, which is 10AX minus 4AY plus 12AZ. So 10AX, 12AZ is here. This is the component value that we got, minus 4, and it is A. Once I got E2, to find the angle, what is the angle? Alpha. The angle will be nothing but the angle between the tangential and the normal component. You know, because we did this, the tangential component and the normal component. So the tangential component is E1 sine alpha. So, and the normal component is E2 sine and the normal component is E1 cos alpha. So your alpha is essentially the angle between them. It is the tan inverse of E2 tangential over E2 normal. And since we know that E2 tangential and E2 normal, we will first find its magnitudes. So these are the magnitudes. And then the angle will be nothing but tan inverse E2 tangential over E1 over E2 normal, which is 75.6. And the energy density, we know it. It is half epsilon E square. So in region 1, it will be E1 square. And in region 2, it will be E2 square. So nanojoules per meter. Got it? So this is how we can find the unknown electric field in the second region. Okay. So I think we will stop here. Any other questions do you have?